incredibly strange things get way down at the quantum level.
Oh, absolutely.
Because, particles down there, they just don't play by the rules we see every day. They act in ways that seem, well, frankly, impossible sometimes.
It's a completely different world, the quantum realm. Our everyday intuition often just doesn't apply.
And maybe the most famous example of that weirdness, the experiment that really, blew the doors off classical physics, is the double-slit experiment.
Definitely. And it's tied so closely to this mathematical idea called the wave function.
Right, and that's what we're digging into today. You've given us this really detailed analysis covering both the experiment and the wave function.
That's the plan.
Yeah.
We want to unpack the insights in your source material, understand how it explains this quantum weirdness, and specifically this whole particles acting like waves thing.
Great, let's crack open this analysis and see what it tells us.
All right. So first things first, to really appreciate how weird the quantum result is, we need to consider what classical physics would expect. The old rules.
Okay, yeah. The source sets up the basic scenario. You've got a barrier, it's got 2 slits in it, something shooting stuff at it, and then a screen behind to see where the stuff ends up.
Exactly. So imagine you're shooting, say, tiny grains of sand, classical particles at that barrier. What pattern do you expect on the screen?
Well, that seems simple enough. You'd just get 2 piles, right? Sand through slit A lands behind slit A. Sand through slit B lands behind slit B. 2 distinct bands.
Precisely. Very predictable. Now, what about classical waves, like water waves hitting that same barrier?
Ah, okay. Waves are different. They'd spread out after passing through each slit, wouldn't they?
They would. And then the waves from slit A would meet the waves from slit B.
And they interfere. Yeah. Where the peaks line up, you get bigger waves, constructive interference. And where a peak meets a trough, they cancel out, destructive interference.
Exactly. So the pattern on the screen wouldn't be 2 simple lines. It would be
a whole series of alternating bright and dark stripes, the interference pattern, bright where they add up, dark where they cancel.
perfect. So classical particles, 2 bands.
Yeah.
Classical waves. Interference pattern. That's our baseline. Now, your source brings in the quantum surprise.
This is where it gets wild.
It really is. Because when they did this experiment with quantum particles, electrons, photons, even whole atoms sometimes, they didn't get the 2 simple bands you'd expect for particles.
And this is the bit that, honestly, always messes with my head. Your source emphasizes they saw this even when sending the particles through one at a time.
That's the absolute kicker. One single particle goes through, hits the screen, makes a dot. Another one goes, another dot. You build it up, dot by single dot.
And the pattern that emerges over time
Is interference pattern, just like the waves.
How can one single particle arriving all by itself build up a pattern that seems to depend on both slits being open? It's like your source puts it really well. It says the particle somehow knows about both slits. That's just mind-bending.
It is completely counterintuitive. And that's exactly why quantum mechanics had to be invented. Your source then brings in the key concept, the wave function, usually written as a Ga, the Greek letter Ca.
Okay, A. The source calls it a mathematical function, not something physical.
That's the crucial point. It's not a wave like water or sound. It's a complex mathematical object.
Yeah.
It involves imaginary numbers even.
Yeah.
And this function describes the quantum state of the particle.
And the source says it holds basically all the information you can know about that particle.
Within the theory, yes. It tells you everything knowable about its properties and how they'll likely evolve. And that evolution is governed by a fundamental equation, the Schrödinger equation. It assigns these complex values to points in space and time.
So it's the math that describes the particle's potential stuff? Behavior.
Its potential behavior, exactly. And how does this AZA help with the knowing about both slits problem?
Yeah, how does it explain that?
Through the principle of superposition. Your source explains this really clearly. Before the particle actually hits the screen and gets measured, its state definitely went through slit A or definitely went through slit B.
It's undecided.
Kind of. It's described as being in a superposition of both possibilities. Think of it like this. There's a part of the wave function describing the possibility of going through slit A, let's call it 8A, and another part for slit B, AB.
Okay.
And the total state of the particle before detection is the combination, the sum of those possibilities. At total, let's say A as in B.
So your source's idea that the particle, in a sense, explores both paths simultaneously. It's not physically splitting, but its state, its mathematical description, includes both paths.
Precisely. The state itself encompasses both potential pathways. It's a fundamentally probabilistic description until a measurement forces the specific outcome.
And like the water waves, these mathematical wave functions, AA and AAB, they also interfere.
They do, mathematically. The wave function AA interferes with A. Where they align constructively, the overall amplitude of A total gets bigger. Where they oppose destructively, the amplitude gets smaller, maybe even zero.
Okay, I think I'm following the math part, sort of. We have this A, it's a superposition, AA plus A, and these parts interfere.
Yeah.
But how does that abstract math turn into, actual dots appearing on a physical screen in that specific pattern?
Right, that's the million-dollar question. Connecting the math to the observation, your source introduces the Born rule here. It's fundamental.
The Born rule.
Max Born figured this out. The wave function A itself, remember, isn't the particle's location. But if you take the absolute magnitude of the wave function at a certain point x in time t, and you square it written, x, t, p, or t, that value tells you the probability density of finding the particle right there at x, if you were to measure its position at time t.
Probability density. So not where it is, but the chance of finding it there if you look. That's a key distinction your source makes.
A huge distinction. A higher value of E means a higher probability of detection at that spot. A lower value, lower probability. If EGS is 0.
You'll never find the particle there. 0 probability.
Exactly. So EGS maps out the potential locations and their likelihoods governed by this probabilistic rule. It's not deterministic like classical physics, where you know exactly where the particle is and where it's going.
That really changes how you have to think about what a particle is before you measure it. It's more like a cloud of possibilities.
That's a good way to visualize it, yeah. A cloud of potentiality described by F, waiting for an interaction.
Which brings us to the screen. When the particle actually hits the detector screen, that's an interaction, a measurement, right? Your source says this is critical.
Absolutely critical. The moment the particle's position is measured, like when it hits the screen, something dramatic happens to the wave function. It's called collapse.
Collapse.
Yeah. The wave function, which was spread out, representing that superposition of possibilities, A plus AB potentially across the whole screen, suddenly collapses down to a single definite point, the specific location where the particle was detected.
So the cloud of possibilities instantly becomes one definite reality upon measurement.
That's the standard interpretation, yes. One specific outcome is realized from the range of possibilities described by A.
But which outcome? Which specific spot does one particle land on? Can we predict that?
Not for a single particle, no. That's the probabilistic part. Where any individual particle lands is random, but the probability of it landing in any particular region is governed by A total over many, many particle impacts.
The overall pattern becomes predictable because more particles will land where the probability A total was high and fewer where it was low.
Exactly. You can't predict the single event, but you can predict the statistical distribution perfectly.
Okay. Let's try and tie this all together now. How does this whole picture superposition, interference of the Born rule, collapse, explain the actual bright and dark fringes we see on the screen, according to your source?
Right. Let's trace it. Particle approaches the slits. Its state is at total AA plus A, a superposition.
Okay.
These wave function components, A and AB, spread out and interfere mathematically as they propagate towards the screen.
Right. Constructive and destructive interference of the math.
Now, the probability of detecting the particle at any point x on that screen is given by the Born rule, Px, A total x plus AB.
And your source mentioned that when you expand that AA plus AB formula mathematically, you get extra bits, right? Not just A plus AB.
Precisely. You get cross terms, interference terms. These terms mathematically represent the interference between A and AB.
Yeah.
And critically, their value depends on the phase difference between AB and that point x.
Phase difference, like whether the waves are in sync or out of sync.
Yeah. Exactly like that. But for the complex phases of the wave function, where AA and EB are in phase, constructive interference, those interference terms add positively, making the total probability, Px, larger than just the sum of individual probabilities.
So high probability spots, that's where lots of particles land over time, forming the bright fringes.
You got it. And where AA and EB are out of phase, destructive interference, those interference terms subtract, making the total probability, Px, smaller, potentially even 0.
Low or 0 probability spots. Few or no particles land there, creating the dark fringes.
Nailed it. So the visible interference pattern is a direct consequence of the wave-like interference of the particle's abstract wave function, combined with a probabilistic rule for where it's detected upon measurement. It's the probabilities that show the wave pattern.
Wow. Okay. That explanation, straight from your source, makes sense of how it happens, even if why it happens that way is still,
Oh, weird.
it is fundamentally weird.
Yeah.
But it's how the universe seems to work at that level. Now, your source adds one more layer of high strangeness, the observer effect. What happens if you try and, like, peek to see which slit the particle actually goes through?
Ah, yes. This is maybe the most profound part. If you set up a detector right at the slit, say, a little light beam that would scatter if an electron goes through slit A, you can find out which path it took.
Okay, so you measure its path before it gets to the screen.
Right. But doing that, the very act of measuring the path, changes everything.
How so?
Because that measurement at the slit also causes the wave function to collapse. If your detector says, aha, it went through slit A, then the possibility of it having been in superposition with slit B just vanishes. It's gone. The superposition is destroyed right there.
So A total is no longer AA plus A, it's just AA if it went through A.
Essentially, yes.
Yeah.
And if there's no AB component anymore, there's nothing for A to interfere with.
And your source says those interference terms in the probability calculation, they just disappear.
They vanish completely. The math for the probability on the screen now becomes just the probability from slit A plus the probability from slit B, calculated separately. PX, AAs plus a BX. No interference.
Which means the pattern on the screen
Goes back to being just two bands, like the classical particles. The beautiful interference pattern is wiped out simply because you look to see which way the particle went.
That's incredible. Your source puts it starkly. The very act of observing the particle's path fundamentally changes the outcome. Just looking changes the reality.
It highlights the incredibly active role that measurement plays in quantum mechanics. It's not passive observation.
Okay, let's try and recap the absolute key takeaways from your source material on all this. It's a lot to absorb.
Sure. First big one. The wave function is the mathematical description of a quantum particle state, and it allows for superposition existing in multiple potential states at once.
Right. Second, these mathematical wave functions for different possibilities, like path A and path B, interfere with each other mathematically.
Third, the crucial link. The square of the wave function's magnitude gives the probability of finding the particle somewhere when you measure it, not where it is beforehand.
Got it. Fourth, the interference pattern, bright-dark fringes, directly comes from this interference affecting the probability distribution a total way. High probability equals bright, low, yield dark.
Fifth, any single particle detection is probabilistic. You only see the deterministic pattern emerge over many events following those probabilities.
And sixth, the observer effect, which your source really emphasized. Measuring the particle's path destroys the superposition, which kills the interference, changing the final pattern on the screen completely. Looking changes the result.
I think that covers the core insights drawn from the analysis you provided.
Yeah. This deep dive, really focusing on your source material, has peeled back layers on quantum mechanics. It's shown how the double slit forces us to accept particles acting like waves, how Hay describes superposition and interference of possibilities, how probability via head dictates where things land, and how measurement isn't just passive watching, it's involved.
It's a clear demonstration, based entirely on the analysis you shared, of just how different the fundamental rules are down there. Non-classical, non-intuitive, but experimentally verified.
So here's a final thought to chew on, stemming directly from what your source laid out. If the wave function describes the spread of possibilities, the superposition, that only resolves into a definite thing when a measurement happens, and if just trying to know the path forces a different reality, what does that imply about the nature of reality before we measure it? And what does it say about the role we, or at least our measurements, play in making reality concrete? Definitely something to ponder after this deep dive.